Well,
Morning.
morning. How are you?
Pretty good actually.
Good.
How are you?
Okay. I'm doing okay.
I've had a lot on my mind since Wednesday and Thursday. So I'll say more about that later.
Yeah. Oh, you mean our meetings, not just in general.
Well, both, but yes.
Okay.
Yeah.
Well, I don't know who else will be here, but I guess we can welcome them when they come in.
Mhm.
So, what are your updates?
Well, let's see if I can share anything of interest. Let's see here. The most simplest way to say things is it's been I really appreciate where we are with the creation feature stuff, and the Neurobinger reading group also has been interesting. It's sort of become almost a low grade therapy session about doing some of the work, like dealing with the points of interfaces that Norbert talks about. And I apologize for it becoming maybe a little bit somewhere between rants and soapboxes and philosophical discussions. It's an unusual reading group,
Yeah.
really like one I've been in before, but the topic and the content are very interesting that way. But we have that, and then also, I mean, every day this week there's been some interesting stuff happening. And I'll say a lot more about cognition features as I pull up some things.
Okay.
I'll share the blog post that I've pretty much finished. The Friday group, like, I think it's been a really nice exploration of things over the course of it. Like, we've had some really good professional development discussions. We've had a lot about what it's like to be a worker, to do career stuff, to communicate. And now we're doing some things with addressing actual, like, bigger issues in the space of VR and, I guess, open source development in general. And I think that's been quite useful. And I actually encourage people to check that out. Like, I haven't if I had infinite time and money and all that stuff, I would basically get somebody just to segment out some of the clips from what we said, because they're quite useful discussions to have. And they're kind of buried in other things.
Right.
And I just don't really have the means to do that. But I'm really happy to be having those discussions. And I think I've been thinking last night and this morning a bit about, I really appreciate this space that you have made for all this stuff to happen. It takes a certain, because like, for people who are new to this lab and they come to it, and I came to it after I went back to school with sort of undergraduate 2.0 stuff, and it's kind of like, okay, there's this sort of quirky digital space. But going from that time to now, it's just been this sense of there's this pressure, and this is related to some. We talked about this in the Norbert Wiener reading group about the pressure to do certain things academically or scientifically, which is quite relevant.
Right.
But also in terms of the really big projects I want to do, like kind of beyond the cognition features, down the road stuff that's on my mind. There's a lot of pressure to do and create things in certain ways, and there's only a few, like, I'm not really a chess player, okay? But some of my friends are, and have told me about stuff, or have seen some things. And I'm going to use a very, very bad analogy, and people can roast me for it. I'll say it very simply. Basically, what I'm saying is like there's really only a few moves or sets of moves or maneuvers that you can do when you're trying to do actually novel, interesting work. I guess I'm referencing to Norbert Wiener. I'll share it here since I still have it up on this thing. Just a second.
All right.
Yeah, let's get all this stuff off of here. Okay, cool. I think I'm not gonna lose. Oh, we're up. I moved the wrong thing. Okay, good. I almost closed out this window. I don't want to do that. Okay, this will work. I guess I'm referencing more than I expected. This chapter 8 of Norbert Wiener's Human Use of Human Being, Role of the Intellectual and Scientist. At least in the second edition, I think might have been changed in the first somewhat. But we had a really nice discussion about all this stuff and like what you can do. And Norbert kind of gets a little soapboxy, heaven save us, about things, and you know, I don't see it as like I see it as sort of an interesting thing to mention, but I guess the point I'm trying to make is I feel like there's such a limited set of things that feel tenable to do if you want to do academic projects that are actually dealing with the forefront of certain things. And I feel like orthogonal has made space to do one of them very well. And it's the open source version of this is sort of, you know, we don't have a bunch of money to do a bunch of things, but we have relative freedom and movement and agility to focus on what we want to do.
Yeah.
And I think that's almost undervalued, or like I continue to realize like the benefit of that. Like you have to like the ability, like, to use some terms out of place, like the ability to actually self-organize some things in a freer space is really good. Do I think that's the way everything's going to change? No. But for getting people into the space to do it, and then developing some stuff, developing ability, developing skills, developing stuff to get into, do other things. Like there's a lot to be said about institutionalization and getting funding for your PhD and funding for the research you want to do beyond that. And Norbert has different, you know, critiques of that process that we talked about on Thursday. But that's been on my mind quite a bit because it's even sort of thinking about the discussions that we've like unintentional therapy sessions that came out of that have been on my mind quite a bit. So I guess I'll conclude this opening discussion by saying I appreciate the space. I appreciate what I've been able to kind of experience in it, and I think part of the way forward is continuing to do that and letting the space be what it is, because I think there are not very many spaces that are like this, and I think it plays an important role, even if it's only one facet of the whole. Like if you want to actually do some of the work, it's only one part of it, but it's a very important part. So yeah, I'll pause for comments before going on to some other things as I get my screen ready to share something else.
Yeah. Well, I think that's very, yeah, there was a lot of food for thought there with respect to Norbert's ideas about science and how, you know, maybe a lot of administrative tasks or other types of things like, you know, studying something that everyone else is studying versus what you think is, you know, paramount to study or what you want to study. So that's always a problem. And I guess I was thinking about like, how does that relate to information and signal and noise? And it's kind of interesting because the idea being that the pure ideal is signal and the rest is noise, which is not necessarily true. But there is this theme about like in academia, people always talk about how much administrative work there is to do, and that it's overburden. It's an overburden. I think a lot of people would agree with that. I think that there's way too much administrative stuff. There's way too much process with respect to other. If you're learning new tools or if you're implementing tools or whatever, there seems to be a lot of process there, and it takes up a lot of time. And it shouldn't be that process should not be your focus as a scientist. It should be on the actual content. Now, it's like the stuff that we've been doing with VR. I've been doing a lot of experimentation, and I have a lot of background in VR. I mean, I know how it works, but I still find myself doing a lot of like tasks where I'm like trying to get things to work, and and that's sort of like the sort of tinkering that's part of the scientific process. But still, you do end up doing a lot of things like where you're doing tech support for yourself or for others, or there is a lot of administrative stuff and like grants or in trying to get from your beginning your program to your dissertation. That's just like I guess you could say it's noise. Uh, so yeah, I mean, there's a lot of that. I appreciated that conversation. Um,
Yeah. But
yeah, but I mean, other than that, I mean, it's really, I think we should revisit that as like more, not so much the conversation about like, if Norbert Wiener thinks it's extraneous to focus on bureaucracy, but rather like, what does this look like in terms of cybernetics? It's funny because like he's Mr. Cybernetics, but we haven't talked about cybernetics in a couple of chapters. So I mean but nevertheless, I think it's interesting to say what does this look like in terms of regulation, because that's what I'm interested in with cybernetics is like the
can you
regulative
say
aspect.
what is a what? I missed that.
Oh, what is it? What does it look like in terms of regulation? So, what is a good model of science that would regulate the information, the signal, and get rid of or offload a lot of the noise? What would that controller look like? This all being cybernetics, right? Like, if it's not cybernetics, that's fine, but like,
And I think that's sort of like where a lot of the rubber meets the road with criticism of cybernetics, or like you could like there's the whole Project Cybersign, this potential of automated, regulated. What does science look like? But what does economy or government look like? And I think the criticism of this basically are, well, that's you having to, someone is determining what the goal is or what to optimize. And I can see criticism of well, choosing that at a certain way, what to optimize or where to steer it. Like a lot of great things in science happen because someone was studying one thing and found an awkward solution that really is great for something else. And it's just like, we're going to say, oh, that's noise, that's useless, don't disregard that,
yeah,
that kind of stuff. I think there's something to, it's sort of interesting in terms of what's the lens, that you want to use. That's the cybernetic lens, like, if there's every good, what is, and this is a very loosely said, what's like every good, I would say scientist, or there's sort of this like what's the good way to do it, and I'm sure somewhere there's someone written a lot about ethics and cybernetics, which is an interesting dovetail for me. Also, hi Amanda, which is an interesting dovetail for me in terms of like one of the things I want to get to down the road is like I want to look a little more into ethics and its relation to phenomenology and embodiment. But that's kind of a separate story. So um, I guess I'll pause here and give space to Bradley to say things, or for Amanda to do like introductions.
Yeah, I'll say two things about this. So, I mean, the first is that I get your point about like optimizing the scientific process. Like that's typically what you learn in like grad school, or there's a pressure to find like a positive result, or to link your result to something useful. And that's a problem because a lot of things you do in science aren't necessarily immediately useful, nor are they positive results. So if you like experiment with something, there's a reason why they call it an experiment, and that's because you don't always succeed. And sometimes you succeed in ambiguous ways or fail in ambiguous ways, and there's a lot to take from that. And so it's like, okay, you got to make space for that, and you have to make space for like how to interpret it. And the other thing too is that we talked about Project Cybersyn and entropy for science.
There we go. Yeah, kind of it.
Yeah, so we talked about Project Cybersyn. See, this is the thing right here: the 19th century versus the 21st century academic or scientist.
Yeah,
I guess.
Project Cybersyn, you're saying? Sorry.
Oh yeah, so Project Cybersyn, where you had this. They basically had a control room, and they said, well, we're going to plan an economy the size of Chile, which is a pretty decent sized economy, and it's planning everything in an economy. So it's like industrial production, agricultural production, oligocracy. Yes, that's the term that they use. And corporations do a lot of that now. Like that, this isn't just something that governments do. I mean, corporations do this quite widely. Like they'll do this for making projections for the next quarter, and so sometimes they make some really weird decisions or unpopular decisions, like we talked about yesterday. But this is the thing. Can you make that? Can you do planning at that scale? What I mean is that is it that you can do? It's not that you can do planning at that scale because you don't have or you can't do planning at that scale because you don't have the right technology. That you just need bigger computers and more sophisticated algorithms. Yeah, that's their control panel, or the better control panel. It's that there are a lot of things about societies and complex systems that are unpredictable or inherently non-predictable. So there's a question that if this enterprise is even possible, given the scale of what you're trying to do. And so this is something I think it's not without, and this of course feeds into tech ethics because it's not without precedent in the real world. If you're like talking about a corporation, they're planning to plan production. I mean, there's a lot in a lot of stuff in the logistics field that it suggests that you can do these sorts of things. But we also know that corporations sometimes have problems handling like events that are unpredictable, like black swan events, like the pandemic, for example. So this is something that I bring up in project management. Is like Project Cybersyn versus something like the book Seeing Like a State, which is a book that basically critiques this idea of being able to predict the outputs of large organizations, large enterprises like nation states or corporations. And it's basically the only thing you get out of it is surveillance. So that's that's the thing. You can think about like planned economies as maybe being possible, maybe not. Maybe some parts of it are possible. The legacy here section of Wikipedia is really interesting because it talks about some of the things that some of the critiques and some of the things. But
and that's I think surveillance is actually a really good point because I've been diving a little bit into some critical theory stuff, and one of the big things is like about prison stuff is sort of this evolution to be constantly, more and more and more observed. And it's quite interesting because to me that's an interesting juxtaposition towards like the other side of technology. If if I guess I'll say excuse me, if totalitarian level observation was that's basically like 1984, right? Is that the one where like everything's
Yes.
like very Orwellian? Yeah. If there's sort of this like, permanent big brother thing overlooking everything you do, the flip side of it is that, which is actually quite related to, again, going back to our Thursday conversation, there's sort of this flip side of I can start a Facebook, social media, Twitter, whatever, live, or stream YouTube live, which I've done for some of the reading group things, and anybody on the planet almost can see it, almost heavily asterisk. And it's just, it's quite interesting, like from an outside perspective, outside of this discussion, I guess. It's so interesting because we're kind of talking about it here, but in like everyday conventional society, it's almost sort of just like, oh yeah, like afterthought, like that. There's just that huge range of it that's constantly there. Like you can get micromanaged, stuff, or you can get this huge open one-to-many virality thing that goes on, and there's not really, and that's not really saying one's good or bad, or just like that is so different now, and I feel like I think that's
Yeah, we talked about social media and some of the demands of content. I mean, I think like like the way we do things in this lab is kind of like that. I mean, it's like different than like a conventional lab because a lot of stuff we do is like interacting on like a in a format like this where we're on YouTube and people can see it. So it's not like we don't make everything public, but like basically the main meetings and then planning those out. It's kind of like you're planning out content in a way, but in the other way, I think of this as like an opportunity to sort of organize things so that they're not it kind of forces you to organize things into things that are digestible. So a lot of times you get these ideas that are very broad and hard to discuss, and you this really kind of forces you to say, okay, I'm going to present this thing, and here's the idea, and then that can carry on over several meetings. So my vision for this sort of format is like, yes, it may be viral in that sense, like you have to prepare content, but it's also an opportunity for pedagogy. It's an opportunity to put together things, to teach out things or work out ideas over several sessions. So I mean, it's not that it's all bad. It's just that like, it's just a different way of thinking about it. And then if you're not intentional about it, it can be that trap of like, well, I'm just putting out content.
Yeah, and that's kind of, yes. And I think Amanda probably has enough context to kind of put together what we started out talking about.
Yeah, it's basically what we were talking about Wednesday and Thursday.
Okay, I saw Amanda's comment.
Yeah, so it looks like she said reading groups are going well. And yeah, she's going to read your phenomenology post. So yeah, why don't I wait for her to read that, and I will, when she's done giving comments, I will look it over and make it go live.
Yeah, I think she's looking at it in the Notion space. I might just go over some parts of it today, and feel free to like give feedback, or if you want to write things in Notion about it, you can do that too.
Yeah, that would be good.
But yeah, like that was the first thing I said today. Was basically it's been the sequence of events from Wednesday with Cognition Futures, Thursday with the Norbert group, and Friday with the open source group has been really interesting, and I'm very fortunate to be exposed to that because it helps center a lot of things, like directions one wants to go in. But yeah, anything else? I think that was Amanda's whole update. Anything else you want to say before we move on to other stuff, Amanda, or Bradley?
I'm okay.
I mentioned this earlier. I guess we'll pull this out and adjust this.
Right.
I will go over the this filter doesn't quite stick sometimes because it just shows everything. Whoops, that's not what I wanted to do. I just delete this. Yeah. There you go. The one to show is not done. So basically, we have robots almost here. That's kind of the main thing I wanted to say.
When is that?
2 weeks, basically.
Okay.
About 2 weeks from now.
So that's like the end of the month?
Yeah. There's a pre-conference workshop that I signed up to go to, which is like they do a nice sort of fun, semi-formal, slightly informal stuff before the conferences. I didn't get to go last year. I might only go for a little bit, but it gotta be a nice way to meet some people ahead of time. And it's all here in Boston, so it's a lot easier for me to do this time around. Yeah, so that's kind of what's on this. There's actually quite a few things that I want to do here that I should put on here related to Computational Futures stuff, but I don't think I want to do that right now. It's kind of just a brief look at what's going on. I did mention, and just to mention this again here in this setting, I think I would like to, and I don't know how, I don't know the best way to do it, but I'd like to keep the Friday discussions going in some form around VR open source stuff. Mm-hmm. Whether we make them part of this Saturday thing or not. Maybe it could be like part office hours or like part discussion. I don't really know, but I feel like it's been a nice mix of especially when like Hussein and Morgan and Vishali and Raj and all the people get there, or even I think Ankit could join sometimes, and like it just having that sort of alternate space that's a little focused on this stuff has been pretty fruitful for discussions. So yeah, a lot more fruitful than the Cyber Sign project was. That's a different story. These are all illustrations. They look almost like this one looks like an illustration.
Yeah, I think it was a lot of conceptual stuff. But
anyway.
But yeah, it's pretty. They had I think a good idea. I mean, like a lot of the stuff that people do now with respect to like industrial planning and logistics are kind of inspired by that, because you're trying to predict. There's this idea of the just-in-time management, where you have things that are just put in, supply chains that pick up something and then just move it, and everything has to be there, kind of in place. And if it works well, it works well. But during the pandemic, of course, we had a lot of problems with like supply chains, and maybe that could be part of the reason why. I've always said that. I don't know if that's true or not, but definitely, if you have a system where there's no slack, you can have like a very efficient system. But if you hit some sort of perturbation, like where you don't get your products in one place at one time, it causes great problems. So this is the thing about like planning an industrial economy. if you have like hiccups in supply chains or hiccups in other things, then that can cascade throughout the system. So yeah, I mean that's kind of even like what Norbert was talking about. This was before any of this stuff happened, but
Mm.
it was I think a decent intuition.
Yeah. So I don't have a lot to say here unless there's somebody wants, and this isn't anything people want to add to this right now. I'll look at the
Yeah.
call comments.
So I finished up the slides for Bika. I have to record the the presentation. So that's coming along. How are the papers for the web conference on philosophy of mind coming? I know Amanda and Jesse are both working on that.
Mine's on hold for another week or so.
Okay.
But it's there. So, if you want to say anything about yours, Amanda, you can.
So it looks like we have a blog post here to look at.
Yeah, oh, here. I'll get to that in a second. I don't really like how my blog's laid out yet, but I'm just not I'm not aesthetically focused right now.
Yeah, that's always a thing. Like the aesthetics are always like out of reach, I think, for a lot of things.
Well, yeah, and it's like I wanted to be simple. Like I wish I could get rid of like the requirement to have all. I wanted to do something simple on WordPress, but then it's like WordPress always makes you use featured images, and it's like I don't really care about
Right.
that.
It's
Like, I don't want to make my stuff overly pretty for things not in this space. For other things that are way more, like if I submit something to a fancy magazine, yes, but here, like, no. So I'm dealing with that. I guess one thing I'll say before I get into that is, I guess I'll shift the discussion itself to sort of cognition futures right now, and for those who haven't really been following along with that, where we're at is, we have a weekly reading group meeting, and we're on quite a deep dive in terms of I don't know. I'll just pull this up now. Sort of like Varelian. Varela's phenomenological quest. And it kind of, this is a decent passage of it here, which I'll get to. I'll just leave this up as I talk if people want to read that part. But the methods project itself is sort of about like what methods are tenable and available for like pushing to speak within the existing way of talking about cognitive science. Like, well, how can we, what are the methods available? What's their philosophical underpinnings and like their bents and why, and what does that tell us? So it's sort of this open world RPG quest, of just, hey, let's explore this stuff. Part of this thing, and this is a very this litany that I'm considering is actually something that I think we've talked about quite a bit. It's just what's actually new and exciting. I don't think I wrote this very well. It sounds like a document of issues, a thing of complaints, a very like Martin Luther. Here are my issues with what the establishment's doing. Yes, sure, and that's that's been done, and I guess what's interesting to me is like I want to start having a little better categorization of what these things are, and then link to them some specific stuff we're doing. In the methods project right now, we have these things like open questions, which I don't think I'm going to show right now. I don't want to get into it that much for the project. but I think some of the things, I'll put it this way: things I want to do down the road aren't making a really pretty list of complaints about cognitive science or that space. But I think referencing that document in the things that I'm trying to do will be important. And I continue to see this, like, in terms of like big grand strategy, big picture, big agenda things. I continue to see, like, I'm kind of currently, I haven't done a lot this week, but I'm kind of exploring the, frontier map-ish related questions about philosophy, science, history, science, how we talk about this, who's doing what. I've dived a little bit into Karl Popper and his, what's it called, like fallibilism or something like that. As sort of, you can't prove anything, but you got to keep throwing these bigger and bigger and bigger challenges at the theories and see what stands up and stuff like that. And just different people in that space. And I'm agnostic. I don't have any fanboy stuff about it, unlike Norbert. But I feel like I'm slowly getting better and better and better at the bigger frame of what it's the question of, I want to do something, or I want to demarcate or identify something. The best way to do that, and it's really tough because it's really tough because there's this paradox, and I guess actually maybe you guys might know about it somewhat. There's this paradox in terms of some of the things I'll it's sort of this paradox of, because stuff has been written and exists and has a lot of inertia, there's sort of this necessity to, well, relative to this, I think that. And I think that's a really important, obviously, thing to do. It lets you build upon stuff. And, we've many discussions in the group about the importance of actually, are you building on theory, or are you just sort of, there's a lot of pressure right now. Well, this is Jesse's brand, trademark, and intellectual property, and my paper and my book of, cognitive science, Jesse Cog Science, my new product, and I have a book on it, and I'm distributing it out, and I'm an influencer about it, and I'm on TV, and I'm really sensational, and I get press, and I get funded to do things, and it's like, oh, Jesse's brand, cognitive science, and it's just like, it's like you can do that, and there's sort of inclination to do that, but are you like actually pushing stuff forward or not? And it's sort of, at the same time, it's I don't know if I'm not really articulating it very well, the paradox between not wanting to reference things and just saying what you want to do or think, versus helping explain where you are relative to other things, versus having to spending your time justifying stuff that you disagree with or whatever. And that's an interesting space to be in. But I don't know. I think there's probably some specific words for what that is. I don't know if they are right now, but that's, I'm in that space a bit. But with that in mind, what I kind of wanted this thing to, I want this to be sort of a tool that will help that at a broader level. Like, I think it might even, there's an element of this, because you could get really, 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 really fine grained with this in terms of, some like technical differences in how you're interpreting some of the data.
Right.
Using a specific method or whatever. And that's cool, but also there's sort of this, I don't know, higher level version of it that I feel I'm having to wrestle with. So that's kind of one thing.
So I'm trying to figure out, this is all very general, at the very general level right now. It's just kind of like, but what is it that we would, like, I assume you're asking for people to contribute to this. So what would be the, like, things that we would, what are the issues basically? So it's like, are they like concepts or methods, or if we, you don't want it to be a critique because there are a lot of critiques. Would it be like, these are the issues and laying them out and then saying, there's a space that we can identify that where maybe there needs to be some innovation, or what is the thing really kind of you're looking for from people?
And there's sort of like a tenable, respectable version of this, and just a straight up what the platonic ideal, what I just like imagine, like straight from my brain, if you will. And I don't really know where to differentiate along the line somewhat. What I would really like to see is just what I would love at almost like an executive summary of the process after the fact would be almost like a summary of really important, for lack of better terms, problems. And by summary, I mean there are many smaller points that would be aggregated into bigger ones. And those problems at a high level would be kind of accessible in saying, yes, we are working on these problems, or even just not even working, but like when we're discussing stuff, like being able to reference easily these problems as opposed to having them be in the background or like, not related. It's sort of like to kind of awkwardly use the analogy of like the elephant and people holding the different blind parts of it and like thinking, oh, what is this? Almost like the guide should be not declaring, oh, we have an elephant, but more like, yeah, there's something really big and cylindrical that's like got this at this location. Like it might be a hind leg or a foreleg or whatever. Like you're identifying the part that's around. Like you're trying to identify what that problem space is, if that makes sense.
Yeah.
Like that's kind of at the high level an outcome that I would like to have. In a what does it look like nuts and bolts sense? I wouldn't mind trying to just, it's almost like a problem literature review. And I'm sure there's a bunch of people doing, oh, here's the biggest issues in cognitive science. And we even talked about the 25th anniversary stuff that was kind of partial with that and seems a little more like, maybe the 25th anniversary was kind of, partly. I think Amanda's popped up here.
Yeah.
This is what I've contact with, and here are the details about assumptions about what animals. Yeah, Amanda, and very much like just putting that in some slightly organized form would be something. Not. I don't even know if I want to make it some fancy document, but like something to sort of problems that act as reference points or not landmarks, but like that. They're basically things by which other things can be related or referenced in a proxemic or that kind of way. And this is kind of, the more I talk about it, the like I can talk about it in a really nebulous way, or I can say I would just like a list of really big problems in psychology and cognitive science and neuroscience that we can focus on when we talk about this stuff.
Yeah,
that's also true. And so it can be that or not. I don't know which version I really want to do with it.
Yeah.
But like it's kind of going to be like a very particular kind of map, or to be a little bit like nerdy in a way that I think Bradley might appreciate. but not necessarily. It reminds me a little bit of like contextual geometric structures, that there's sort of just this reference point, reference space that isn't really a thing, but you're making this like problem space that you can tag other things to.
Yeah.
Something like it's like a layer or problem dimension that you're just tagging some stuff to. Not in the sense that I want to be what's it called? I don't want to micromanage data, and that's a big thing. That's been a major thing that I've been doing with the last year or so. I was like, because it's there's, for people who care about categorizing data or attempts at data, you can go, wow, you can make all the notion tests and issues in GitHub and like all this track this stuff. Is like, to what end, and I don't really want to do that, but I'm feeling a use. I'm feeling a use for this because I'll just put this here.
So I guess, yeah, my understanding of it is it's not like a conventional critique, and we've talked about those, but it's kind of like, what are the problems going forward? Which is kind of hard to know if you're not like at the crux of like a subfield, like.
Right.
So I mean, there is this aspect, like if you're in like consciousness studies or consciousness science or whatever they're calling it, and you say these are the problems that we have in the field, and you can do a literature review on that. That's actually not what you want either. It's just to say, like, what are the things that maybe open areas that people haven't talked about, or maybe like if you have three intersecting fields, what are the points of intersection, and have people kind of dealt with have people worked on problems in those areas?
To be overly simplistic, it's another version of frontier map related stuff.
Right.
Like it's getting at that, and I don't really think the solution's that different than like there's a version of this, like one version of this project taken to like all the way out would just be like a discussion series specifically about this across things, where you talk to people in different fields and talk about what is that there, and just continuously bring up that context. Because I don't desire to write a definitive thing about all these things, but I also feel like part of the work of all this stuff that I'm kind of talking about is like, how do we, and part of, to go back to like this, the blog post in the Borrellian lineage of looking at phenomenology and mutual constraints and stuff like that is, just, I feel like, I guess it is not surprising that this is niche stuff and it's not accessible. You kind of need to know stuff, and you can't just say it. At the same time, I feel this massive urge to make this stuff tenable, because people don't, if you're not, you kind of have to understand where the things are and can be. So I don't know, like, let's see what Amanda's saying. Amanda says there's a difference between one, problems within the field. For example, neuroscience of consciousness deals with network science, and there's questions about which areas of the brain drive certain network activity. And two, problems with the field, I think pukes on why the brain isn't the only location of consciousness, casting doubt on 3P methods as a whole. Yeah. So she's saying basically problems within the field and problems with the field. And I think I think there's probably a really nice somebody probably somewhere in like Thomas Kuhn's books that I haven't really dived into much, or other people have ways to talk about that very well, and I don't know if they are yet. And I think what I would love to have would be a problem space that's field independent, and then a contextualized, here's where, okay, well in neuroscience, here's what we're dealing with, here's what the fMRIs can do and can't do. Here's X, Y, Z, and this, I keep referencing the brain dance because I feel like brain dance is this tool and set of things that just I don't really know if it's possible, but I find referencing it as not in a sense I want to make it, so I don't know if I do, but more the distance from it seems quite useful to think about as almost this like reverse landmark. So anyway, yes, thank you for that. I'm gonna put that in Notion.
Yeah, do that. Yeah, I think that's an interesting distinction, but I still guess I'm just kind of getting a feel for what you're looking for. You're saying that it's not a critique necessarily, although maybe it could be. It's finding open areas, like what's the landscape, what are the open areas of inquiry, and maybe like a critique generally of like how people tend to focus on certain things and not others. So it's like a field attention or something. I don't know what you'd call it, selective attention, but for a field instead of like a personal environment.
Something like this. I mean, it's the exact form for me isn't finished, and maybe I shouldn't have posted it yet in the sense of there's nothing ready for it to do.
Oh no, I think we should talk about it more. It's a pretty hard concept to get your head around, I guess.
Yeah, and I appreciate I get you're doing that. And I appreciate that you're willing to do that. I feel like, and part of to be frank, like one of the challenges here is that in order to put a coherent lens on all of this, you do basically have to suggest, like you have to optimize towards a direction, even if that's not really what I want to do. Like I have to pick some concept or a narrative around which this will all make sense, or at least be like communicable in an artifact sense. So what is that going to be? And I feel like what that is basically in an ideal sense, and I don't think when I say ideal sense in this way, I almost mean like what I would love it to be, but I know it can't be. What I would love it to be, but know it can be, is like a something that will identify sort of the gaps between what's tenable right now. What it's kind of like what Amanda says, or like what in the fields as they are right now, what are the problems? But also in the effort of understanding, I would say consciousness, which I don't really care to say, in the efforts of understanding other bigger problems, what are the shortcomings? Yeah, the bridge analogy kind of is an interesting thing. I think that's a good thing to reference here. And again, like I need to write down like what is the bridge analogy? I want to write a post about that so we can talk about it. But bridge analogy basically is, as I've said a few meetings ago, is saying, oh, you think, okay, well we want to move, but we know, or I think I'm going to move. I want to move, 100 yards to the left, 100 meters to the left. Okay, well, we tried that. Hey, we can't move, we can't do it. Nobody can move 100 meters to left this position because it's just not there. And the bridge analogy is like, okay, is it not do it? Can we not do that because it's we have tried the solution space, or is it because there is no particular understanding of it? Like, can we move there 100 meters to the left if we build a bridge over the obstacle? Yes or no? Versus, well, given what we have right now, given the effort, we cannot go there. And just sort of that, I did a very bad job of saying it here, but articulating the difference between this is an explored space with explored solutions that we're aware of versus this is something that we maybe even rightfully know that, yeah, you can't really do this. It's not, it's like in order to do this, you're going to have to totally contrive, the law of gravity and most of physics that do this. So you can say, yeah, that in like science fiction universe that we talked a little bit, but in like, it's just breaking too many things we know to go there. It is like that tension between, to an extent. That's probably really incoherent and doesn't help to the discussion we were just having before. But I guess I'll just say, I think I really hesitate to say lofty aims because I don't find it to be useful to do, but to communicate it, it's like, identifying what are the problems in the field, but also what are the problems, like, I'm cringing as I say it, but like, what's the problem in making, human level AI or AGI, or in how far away are we from making a brain dance or making some, shared targeted environment, or fully mapping out, like, I don't know, like whatever, insert your lofty thing that you want to do. And like, I feel like I kind of have to put it, I would like to have a better thing where I can say, actually, this is the goal I want to work towards. And in that lens, here's the problems in the field. And then here's the problems between the fields that we need to work on, and like the bigger structure.
Right.
And then we can move towards this end. Like, I would love to do that. I just don't, I have varying degrees of comfort with each of those components.
Well, yeah, just build a template. I mean, like, so this question, how far are we from AGI, is, as much as that's a non-answerable question right now, I guess, maybe build a template around that. Like, maybe we can answer some aspects of that. And then that's a good, I mean, maybe we don't say AGI, but we say, like, do we understand intelligence enough to build artificial intelligence? Or can we call artificial intelligence artificial intelligence? Something that, I mean, if I say, how far are we from AGI, that's kind of a false question because it assumes that AGI is a thing. It assumes that we can get there from here. And so there are assumptions in your question sometimes that are not warranted. Like, you can't say, I can't say, like, why did God create the brain? Because that's like assuming that God created the brain or something like that, or, sometimes assumptions are warranted. This is the current, like, sort of, sometimes assumptions are the current sort of standard of the field. But most of the time, you don't want to start with a bunch of assumptions in your question. You want to be very much like, this is a thing. Maybe like if we start with, we're in cognitive neuroscience and we say, is cognitive neuroscience something we're going to learn about brain function from? And we say, well, obviously, but not really, because we don't, there are debates right now about localization versus networks, or, things like that we've covered in the meeting that, but those are things you can cast your net around and you can say, oh yeah, there's a literature on that. There's certain things people haven't touched. There are things that we have, limited knowledge about, but we could have more knowledge. Or we have limited knowledge, but it's just intractable to really kind of come up with a way to get more knowledge about this. Like, we were talking on Wednesday about, like, how they do a lot of phenomenology, which is interviews and asking people about their memory. And of course, doing that is a problem because a lot, like Amanda said, you can have false memories. You can conflate things in memory, and that's a limitation of that method. And it may be that method is ultimately totally not tenable because you're getting this giant circle. So that's the kind of thing you get sometimes with scientific methods, or with different methods, is that it just leads you into a giant circle. It's tautological, that ask a question, you try to answer the question, but you actually go back to the question because you implement it in a way that's not it doesn't really answer the question very well, or brings up more problems than it solves. And that you could say arguably some neuroimaging methods are like that, or where we want to, we think, well, that people used to think fMRI was like the problem solver in terms of like brain function, and we probably now know that that's not really the case. But what is the utility of it? There's maybe some utility in something that isn't like necessarily the best method, but what are those points of utility? I mean, I'm just trying to think of this in a concrete way. Um, but I think that would be a way forward, because if you don't have a template for people to follow, it's like people aren't going to be able to contribute to it.
Yeah. Thank you for mentioning all this stuff and taking notes. Yeah, and I appreciate all this discussion. It's helping me think about it, because I feel like, yeah, I realize I've realized something very important to this. I'm not going to say it because it'll be a little it's outside of the scope of some things, but this, yeah, very much all of this has been very, very helpful. So I can continue on with sort of my stuff. I don't know if you want to. I see Amanda writing stuff, and I don't know if you want to say any more, Amanda. Eventually, we'll just go through the blog post thing, but I'll give a pause to people to say the things. Not me talk so much right now.
But why don't we go over the blog post when it's published? I mean, it's like,
okay.
Yeah.
It's already an hour ago,
Yeah.
so we can move on to the things. I appreciate the discussion.
Oh yeah, I think it was good. I think that needed to be discussed, because it's like, we've been trying to do this stuff with cognitive science, and it's been like really hard to. We wanted to do the special issue talk about that. That was from last year, and we were going to have an event, and we couldn't do that. We didn't really get together on that. But I think those are like critiques of the field, which are fine, and we should talk about those. But on the other hand, I really want to have something that's like our own imprimatur. It's like our own stamp on it, where it's our own flavor of it, not just saying, well, this is a shitty paper because, and then it's not a. You know what I mean? Like, it's a little bit more productive, I guess, in terms of
right, moving towards an actual contribution of something.
Yeah, nutritional value, I guess.
I'm curious, like, what I think we're doing some ground. Like, I think about the paper pyramid for cognition futures and that whole, like, the big agenda. But I'm curious, like, we don't have the discussion now, but basically a sense of what, like, I don't know, what are our leans in that sense? Because as in what might that contribution from us look like? I see things about cybernetics. I see things about interpreting Varela's quest line. I see things about combining some of the agent-based modeling and ways of testing these things, and how we want to kind of push and pull different aspects of like phenomenological stuff. That's kind of what stands out to me in things we talk about sense.
Yeah, we should put together. Yeah, we should probably put together. Or I guess I could do that. Put together like a list of things that we've done and how we might move forward, because we're always like exploring new vistas, and that's what happens often. You have to find like new angles on things where you can contribute the greatest amount of stuff. So I think it's time for me to go back and look at what we've done and say, here's some things I think are great ways to go forward on this. But
Yeah, yeah, and like I guess I'm curious. Like, do you see that as like a project or a paper, or more just like here in the lab are views that we think are principles we want to center around?
well,
I don't know.
I think principle wise, we should have some focus. Like I want to.
Mm.
We do these we do these meetings, and we have like this flow of kind of ideas, and we fixate on some things, and then there's this higher level of like, what are the projects that we're going to work on to realize some of these things. And I know we're doing some things at the paper pyramid, but I think it also has like, like sort of synthesizing some of the things across areas. Like I think we talked about agents of phenomenology, or like computational agents, not like, agency, or something like, metabrains and some other aspects of cognitive science. We came up with the metabrains idea. We've written a couple of shorter papers on it, but I think there's some utility in like exploring how to fit in models together. Like the idea of metabrains is that you have these different layers of representation or representational complexity. And so the question is, how do you fit these models in and how do they interact? Which is something we never dealt with in the paper. Or it's even broader than that. Like we might say that there's like we had this discussion in the cognition futures meeting about how we have like this sort of subcognitive level, which is where we have automatized behaviors and instinct and hormonally driven behaviors and emotional behaviors and things like that, versus like the sort of the cognitive world, which is like the intentional world or whatever. And I know that's like kind of a simplistic or overly simplistic dichotomy, but like you're basically, you have these two streams and you're linking them together somehow. And the question is, can we implement that in a meta brain? And if we do that, is it like computationally tractable for like an agent that we could run in a simulation, or at least simulate some of the parts of it? And then conceptually, it's a value because we can build this sort of tractable brain that does something that's, has a behavioral output, perhaps. Maybe can, I don't want to say think, but can, you know, basically produce some sort of output that isn't random. I don't want to go in the direction of saying it's a thinking machine, but it does the things. It does something with information that's sort of like intelligent, like so.
So what immediately comes to my mind for this that would be interesting is relevant to like the screen, is sort of one thing on my mind. I don't know how to fathom it into a computational model right now. Would be shifting the agent's ability to have, I'll say, affectivity, or just the means by which you can be aware of certain internal processes, and how that would change. It's what affectivity is available for it to make cognitive choices about. It's kind of taking the problem we've been talking about, and then we've been putting it. Okay, if we center this as, well, it'll be kind of like playing around with the idea of, you know, let's test the difference in behavioral outputs if it's has a almost no perception of its version of the quote unquote cardiovascular system, versus a really high emphasis on that, like none or higher, none or spectrum, and being able to change those things and what that does. That would require a lot of different things, but there's ways you can get around it. But stuff like that would maybe get at some really simplistic principles of degrees of awareness, and then control and playing around with the agency and all that stuff. So that seems like a space to combine it. I'm not saying we have to do that, but
yeah. Let me move on here. So I don't know if people have like questions about things before we move on or not.
I think that was kind of a big trickle into other things, but yeah. It's nice thinking.
So what I'd like to do now is go over a little bit about some of the Slack channels. Let me see if I can share my screen here. So we've had a fair amount of activity in the Slack channels, of course, the cognition future stuff and the reading group and all that. We've had some interesting activity in brain organoids over the last couple of weeks. We had some organs when working on posting things here. Again, the human embryo models grown from stem cells. We've talked about this in DevoWorm, for example. So we have, we talked about human embryo models and more generally primate embryo models. And these are really fascinating things. They go up to like day 14. They're synthetic models, so they're not actual. I don't know if you could say that they're actual embryos, but they look like day 14 embryos. And there's a process of differentiation that mimics embryogenesis up to day 14. So this is day 14 in human embryogenesis. So this is pretty early, but still you get some structures that form. And so there are a lot of ethical issues around this, and there's a lot of technical issues around this. And it's really a fascinating area. So that's there's some news about that, but I would suggest if you're interested to explore it more generally. This is a nice article. This is a nice video from the Nobel Prize winners on CRISPR, and they talk about how gene editing works using CRISPR. So that's a nice instructional video on that if you're interested. Then I don't know what this link is, but let's see. There's some stuff on regenerative medicine. This regenerative rehabilitation and training network. So they're involved in training and education about regenerative medicine. This is brain organoids could reveal origins of autism. This is a nice overview of different things that we can do with brain organoids. So in the DevoWorm meetings, we kind of had this typology of different models. So we have these organoids that are, you grow them from stem cells and they differentiate into different tissue types. And they form basically organoids, where you have like things that look like organs. They're differentiated tissues in this mass of cells. And so we can culture these in 2 dimensions or 3 dimensions. And they're different types of organoids. So you have brain organoids, which mimic different parts of, different tissues in the brain, different parts of the brain. You can have some sort of you don't really have motor control, or you don't really have emotion, but you do have these structures that are different types of cells you find in the brain. You can also have things like things that are analogous to liver or the heart or things like that. So similarly, they behave like the organ that we're targeting, but they're not the organ that we're targeting. It's just the differentiated cells you would find in that organ. Then you have things like gastroloids, which we talked about last week at DevoWorm. And gastroloids are these structures that mimic gastrulation in a lot of embryos. So this is a very early stage of development. And we can actually find we can actually mimic that pretty well in terms of tissue types. So it's really exciting. There are other types of embryoids that are not organoids, but they're sort of developmental in nature. So, you don't just reproduce the tissue types, you actually reproduce this process of development, or it mimics what you would see in an early embryo. So this is all a very interesting area. Actually, last week I talked in DivaWorm. If you go to the second half of the meeting, after like the hour mark, I considered a case where we're modeling embryoids, and in this case it's specific. It could be specific to embryoids. It could be all organoids. But I've had a number of discussions with people about modeling organoids and embryoids, and I think there are a number of unique challenges, which I mentioned in the video, that are involved in this. So, to recap briefly, you have a bunch of stem cells, which you would just model as like a bunch of nondescript cells. They would be cells with like a body, and they'd have gene expression properties of a stem cell, and they'd be kind of in the same location, bunched up in a ball. And then over time, they would migrate outward, and they would differentiate, and they would communicate with each other. They'd have like long range and short range signaling, but they'd form this. In this modeling world, we would form a sphere eventually. So we'd form a sphere, the cells would move out, they'd proliferate, so they'd divide. They'd express different genes, so they would have some sort of gene regulatory network inside of them. And they would change their state. So eventually they'd go from a stem cell to some other cell type. And they might go through different stages or different intermediate cell types, but they end up at some point. So this is a modeling exercise. It's not meant to be like a one-to-one mapping to the biological system, but in any case. So these, then you have this differentiation, you have these different cell types, but then, you also have to have bioelectric properties. And this is something I think, if you were modeling like a neural organoid, you'd be interested in action potential generation. But as we know from the work in bioelectricity, all cells have a biological or have an electrical potential. And it's because they all express ion channels of different types. The question is whether they can actually put together a coherent action potential. And so we can model, do biophysical modeling of the cells, or build a biophysical model that's very simple so that we can mimic these changes in state. So again, it's not just the change in the physical state of the cell, the phenotype, and the molecular profile, but also the electrical activity. And so that's kind of where we are. We've not been able to implement anything. I've had these discussions, and then I guess it's too not worth people's time or whatever. But I don't know. I mean, if people want to pick this up, it's fine. I would love to see it. I don't know if we could make this more relevant to some of the other stuff we're doing, but I certainly think it's worth at least thinking about.
By pick it up, do you mean like doing more with?
Well, I mean, working it into like a actual computational model of some type. Like, this is all just kind of like, kind of a theoretical thing now. We haven't implemented it in any sort of type of software. So that, I mean, the idea would be to implement it in software and do simulations and see what they look like, which would be interesting, but we haven't been able to get to that point. So to pick it up as like a project that someone would want to drive forward.
Pretty organized stuff in general,
yeah. Yeah. Well, go ahead.
Oh, go ahead. No, you.
Oh, yeah. So that's a lot of stuff we're doing with organoids and the current thinking in the group. And beyond that, we don't really do a lot of biology, but Morgan and I have talked about like some of the possibilities there. And so this is still kind of up in the air as to how this actually works out. But I don't know what we can contribute, but there's got to be something. Got to be some way. And we're doing good. Like we're doing some good synthesis here on the channel. That's why I like to talk about it in the channel, because it's like Organoids has these wonderful things he finds and puts them in here, but I don't think we kind of have a lab-wide appreciation for it. So Diva Worm, we talk about it sometimes, but it's kind of hard to kind of get some space in there because we're doing all sorts of things there. So this is the stem cells and clinical genomics for clinical trials in a dish. So like a lot of the stuff with brain organoids, people build them primarily to study disease. So you're interested in disease, and having analogs like animal models are important, but also having analogs like cell culture models are important as well. And cell culture models conventionally are not very good at like capturing the geometry of the tissue and some of the other sort of native behaviors of tissues and organs. Now, organoids bridge that gap somewhat, so this is why it's kind of cool to have like just to think about it as a computational model, because it's like we can even from there we can learn things just thinking about it in a new way. So this talks about clinical genomics, which is of course where you're trying to find the genes for things that like diseases and other things. So this is really cool stuff. Yeah, I mean that's brain organoids. We've had a couple things in different other channels like Cybernetics. We've kind of got I haven't talked about this channel in a while, but we've talked a little bit about some of the sort of the history of cybernetics, but also modern implementations like sensory motor neuroscience, sensory motor behavior. This is a paper on embracing sensory motor history, which is free energy principle related, but thinking about sensory motor integration, sensory motor behavior as this sort of time series. Like papers like this really kind of I think kind of allow us to break free of like the conventional way we view things like sensory motor control, because we tend to think of it as like a very immediate thing. Like you see something, you reach for it, and it's like feedback, and then that's pretty much it. And you might have a memory of it later, and then you have this automatic behavior. Sometimes you have to learn behaviors so they become automatic, and then you can make these seamless movements towards an object. But to kind of like get in more into the time aspect of this or the temporal aspect of this, so I think it's in a kind of an interesting paper. And then this paper Amanda posted by Rosenbluth. This is the classic paper in cybernetics. It doesn't get talked about a lot, but it's still so it's behavior, purpose, and teleology. So Norbert Wiener is on this paper. Arturo Rosenbluth and Julian Bigelow as well. And this is kind of a classic paper. We haven't talked about too much, but it's like one of these papers that is under the surface of our understanding of cybernetics. Basically, this idea that there's, in cybernetics, we have behavior, we have this idea of purpose, and this idea that time is ordered in some ways. So, this whole idea of purpose in like behavior and I don't know. I kind of am on the side of purposelessness because I think it's not. I think we're kind of projecting things onto some of these systems where we say something has a purpose, and it's very functional. It's very appealing in that sense. But like, I also think the case could be made for purposelessness.
Well, and I think I resonate with that in the sense of I'm trying to find the language that I want. I want to have a language where I can say it's really tenable and graspable and easy for us as human beings in how we are.
Yeah.
See the lens of purposefulness. That's not the same as this is the actual mechanism that clinically is putting stuff out there. I don't really know how to talk about that very well.
Yeah, it kind of there's this temptation to anthropomorphize things, like you say. Well, this is obviously purposeful because it's like kind of like when people say something is it well adapted to something, or they say that obviously behaviors have a larger goal orientedness, but unless it's like an immediate goal orientedness, and we talked about some of the stuff that Tinbergen talked about with proximate versus distal causality And, like there's approximate causality, which is me doing things in the world. And then there's a distal causality, which is like development or evolution. And then I think, in both of those, I don't necessarily think purpose is like the thing that we need to think about. We need to think more about like purpose is not being the sort of the default hypothesis. But in any case, this paper talks about this, and it's classic in the sense that they bring this up in the sense of cybernetics. So they talk about a lot of things. If you're interested in knowing like why neuroscientists think the way they do about like goal orientedness and things like that, this is really, I think, a Rosetta Stone for this, because it kind of gets into this whole idea of feedback as like purposeful behavior. And so, like, if you're talking about cybernetics, that's kind of a core concept. And you have this this way of kind of thinking about predictive behavior. We talked about predictive processing. All those things kind of go back to this. So it's really kind of, and they even break it down into this hierarchy, or this, I guess you could call it a subsumption architecture of behavior. Subsumption architecture means it has like a nested quality. And so that's what they use in AI a lot, or classical AI, the subsumption architecture. This is where you have behavior, and then you break it down to active, purposeful, teleological feedback, which means it has this structure with respect to time. And sometimes you have non-teleological feedback, and then non-predictive versus predictive, and then different derivatives of prediction. So this is something I think, this figure here, really, I think we should think about this more, because, like people tend to think of, or at least the part of cybernetics that's gone forward from this paper, is that you have, maybe like active behavior, it's purposeful, maybe feedback is teleological, and then we have this predictive quality, and then we stop here. And like this part is maybe in something like predictive processing, maybe not. So I mean, what happens if we have like these non-active or non-purposeful things, non-feedback, or feedback that's non-teleological? I don't like this distinction necessarily. And then non-predictive, and then like you have these sort of, and we talked about timescales in cognition. You have these derivatives of prediction. So you have predictions of predictions, where you have like, extrapolations of extrapolations. What happens then? And I don't think people talk about that much in modern cognitive science, like these sort of derivatives of behavior. And that's something that I think it's too much to go into here, but I just want to put a pin in this thing here. Hope it's in the notion.
we are assembling things in there right now.
Very good. Yeah, this is great. Yeah. Thanks for putting this in here, Amanda. It was good for thinking this through a little bit more. And that's kind of what I want to do here. This is another paper I don't think we've talked about ever like in the meeting, but this is a paper I posted it like 2 months ago, but it's going back to like neuroscience and cybernetics. So like we typically think that neuroscience borrowed from cybernetics is kind of like from cybernetics to neuroscience. But this article, and this is I think by a couple of some Spaniards talking about Spaniards, that Spanish neuroscience, I guess, gave birth to cybernetics, which is not the way we think about it. So like, you had some things going on with Ramon y Cajal and Laurent Dino in terms of like putting together what maybe like neural circuits look like, or neurons. So this is kind of what Ramon y Cajal was doing, and at the turn of the last century, he was drawing like these networks in the cerebellum, and kind of talking about some of these things, how we have these recurrent structures in the brain. So we have these systems that come, go down in layers and come up, and so there are these really complicated dendritic structures that do processing. And so there was no language for this. There was no cybernetic language to borrow from. So they had to kind of come up with their own language, and they were just drawing things out. The thinking of like what we saw in the 1943 example wasn't around yet. But so there, and then, people were observing things like spinal reflexes. So there was this whole science of, oh yeah, there's this thing that's recursive or circular. And so that needed to be captured. And so, as far as I know, like cybernetics really didn't talk too much about the brain as like a set of examples. I mean, you see it in like neuroscience later, but like, or in cognitive science maybe later. But this is not something that was immediately pulled together. And so this paper talks about some of the precursors and how they actually serve to inform what we think of when we think of neuroscience. I mean, we did have, of course, have the classic examples, of sort of our neurophysiological neuron, which is now this, like circle and connection, sort of connectionist, the origins of connectionism and things like that. But this is not what I'm talking about here. This is actually just kind of like this old school neuroscience where they weren't thinking about any sort of computational structure. They weren't thinking about the synapse necessarily. They were just thinking about these large scale structures. So yeah, then we also have let's see, we have our computational psychiatry, which we talked about a couple weeks ago, and Morgan's been putting things in here. There's been a lot of stuff since we last visited this channel, so this is something, if people are interested in following, they should follow it. There's a lot of really interesting stuff in here. There's this paper on disentangled representation learning, which is on, so this is DRL, aims to learn a model capable of identifying and disentangling the underlying factors hidden in the observable data of representation form. So this goes back to some of the causality stuff we were talking about. This kind of categorizes methodologies for DRL into 4 groups. Traditional statistical approaches, variational autoencoder-based approaches, generative adversarial network approaches or GANs, hierarchical approaches, and other approaches. So these are like these different categories that they use to kind of, they draw on some of the methods that we use today, but they're still kind of like putting it in a different set of categories. So, this is kind of talking about this as like almost like universal learning and, kind of going, this is a nice paper. There are other papers in here as well. We have a lot of stuff on like neuroscience and disease, and the UK Biobank, and some issues with respect to health data and health information. Oh, this one here, development of sensory motor visual connectome gradient at birth predicts cognitive outcome at 2 years. I think I saw this paper earlier, but this is really cool. This is where we're looking at the developmental connectome, and actually at this point at birth, so it's pretty early. Which, of course, if we know that the sort of the visual system, we're born with many more synapses than we use in our later in development. So there's this process of pruning synapses, and so this is kind of a interesting paper in that respect. That we have this process of pruning, but we can also take this developmental process and predict cognitive outcomes later on. So it's a longitudinal study where you're looking at different aspects of their cognitive, postnatal cognitive growth. So this is really interesting stuff. Yeah, this is a good paper. So yeah, Morgan, you've done a really good job of putting together some of these readings. Now I'm archiving these channels, so we have these archived. It's not like going into the ether. I'm not necessarily sharing the archive because I don't have a place to store it that we can share the files, but I can talk, if you want a certain archive of it, I probably have it. In any case, I think this is a nice overview of our Slack. But I wanted to move on. So if you have any questions, now's the time.
No questions, but I appreciate the review.
Yeah.
Yeah, I had posted that Cybernetics Rosenbluth paper and then immediately forgot about it. So
yeah.
glad to go back to it. And that talk that Levin mentioned it in was very interesting too.
Yeah. I mean, it has tentacles. I'm not saying that I'm saying that it's basically the basis for a lot of our conversations today on, the way behavior works or what we should expect out of intelligence. So definitely an important thing to understand the base, the sort of the grounding of that. Because I think a lot of ideas are grounded in things from maybe 100 years ago. People were talking about things and they kind of developed out of those things. And so our concepts are really grounded in a lot of these older concepts, whether they're maybe pre-scientific or carryovers from pre-scientific era things, or whether they're actually pretty solid things that if we replaced them, we would be lost. I don't know.
Mm-hmm.
Right. All right. So let me move on. So I'm still sharing my screen. So a couple weeks ago, we talked about energetics in the brain. I know we were kind of interested in that, and then I kind of paired that with a paper in predictive processing, which we talked a little bit about. And so this is a follow-up to the energetics discussion. I have 3 papers here. I'm going to go in no particular order. Let me see if this is the right one I want to start with, though. Okay. Yeah, why don't we start with this one? Okay. So this is where we talk about, the title of this paper is Signatures of Bayesian Inference Emerge from Energy Efficient Synapses. And so we have this idea of Bayesian inference, which is, of course, a common idea in neuroscience, or that's been adapted in neuroscience. And I couldn't point to the sort of the foundational paper for that, but it is a foundational idea. So the idea that Bayesian inference is the key to understanding how the brain works. But anyways, this is a statistical statement. So this is something that we impose upon what's going on in the brain, what's going on with behavior. But what they're arguing is that there's signatures of this kind of inference emerging from energy efficient synapses. So this is where they're arguing that physiology and energetics produce something that looks like something that we've come up with, quite independent of that process, but is, I guess maybe better way to say it is that explains it. But you'll find this kind of way of thinking about it a lot. But in any case, the reason I mention that is because, I want to make sure we understand that it's not that nature is creating Bayesian inference to conform with our understanding of how the brain works. It's that we find a model and we say it predicts the natural system well. And maybe not too well, but well enough. So this is an important distinction to make. So the abstract here reads, biological synaptic transmission is unreliable. So that means that it's not perfect, or it's not optimized necessarily, but it works. But anyways, it's unreliable, and this unreliability likely degrades neural circuit performance. So we think about physiology sometimes as being highly efficient, but in this case it's not, and it's unreliable in the sense that it's not totally predictable, but it works well enough to allow for thinking and for physiological function and all those things. So it can degrade neural circuit performance, and that's why we have circuit disorders, and we forget things and other things. Well, there are biophysical mechanisms that can increase reliability. For instance, by increasing vesicle release probability. These mechanisms cost energy. So basically, you have a system that's not perfect, and it's because evolution is not really an optimizing process so much as it is, it selects things that allow for survival, but it's not an absolute thing. So, like, sometimes you have things that are good enough that get selected for an evolution, and you end up with, basically good enough stuff that works maybe unreliably, but can be improved upon by other parallel processes that can compensate for things. You see this a lot in evolution, actually. So we have biophysical mechanisms that can increase reliability. These mechanisms cost energy. So there's an energy cost to improving upon the unreliability of synaptic transmission. There's an energetic cost of synaptic transmission. We examined 4 such mechanisms along with the associated scaling of the energetic costs. So this is where they took 4 candidate mechanisms and looked at the scaling of costs. We then embedded these energetic costs for reliability into ANNs, artificial neural networks, with trainable stochastic synapses, and trained these networks on standard image classification tasks. Okay. The resulting networks revealed a trade-off between circuit performance and the energetic cost of synaptic reliability. So this is where they tested this in ANNs, which maybe aren't like ideal, but you can get a sense of the energetic cost. You can encode the energetic costs and just make assumptions about it. The resulting networks revealed a trade-off between circuit performance on the one hand and how you can improve synaptic reliability. So basically, if something is always perfect versus whether it works well. And so there's this, basically found the same relationship here. Additionally, the optimized networks exhibited 2 testable predictions consistent with pre-existing experimental data. So these 2 testable predictions are that synapses with lower variability, meaning they don't vary as much, tended to have 1, higher input firing rates, and 2, lower learning rates. So they're like kind of faster, but also lower learners, or they have lower learning rates. So that means that variability plays a role here in how synapses function. It changes the way that they behave, not just that there's variability because it's noise or something like that. I mean, there's the role for noise. Sometimes the role for noise is positive in systems, not just negative. So we go back to like cybernetics. We talk about noise and signal as always being like this idea of signal being good and noise being bad. But sometimes noise can be good. If you think of noise as variability, it can lead to different types of physiological outcomes. And it can actually buffer some of the systems that are imperfect. So, it can train a system where you don't, you train it on a bunch of exemplars and then you add noise. And the noise allows it to generalize more. Surprisingly, these predictions also arise when synapse statistics are inferred through Bayesian inference. So this is where we get to the Bayesian inference part, where we can have these same predictions that arise then. Indeed, we were able to find a formal theoretical link between the performance, reliability, cost trade-off, and Bayesian inference. So Bayesian inference is basically predicting this model or this theoretical link. This connection suggests 2 incompatible possibilities. The first is that evolution may have chanced upon a scheme for implementing Bayesian inference, by optimizing energy efficiency. So this argues that evolution is maximally energy efficient, or maybe energy efficient enough in a way that's optimizing the system so that Bayesian inference is possible. Now, when they say Bayesian inference, they don't mean that it's like conscious Bayesian inference. It's just like that type of thing. So it's weighing prior information and integrating it. So, in terms of that, we know about neurointegrators. It's not like that doesn't exist. It's just that, this idea of Bayesian inference is more kind of it's more kind of a mechanism, a way to describe the mechanism than that the system actually uses Bayesian inference as a formal framework. But the idea is that evolution may have done this, optimized it enough to be, energy efficient. Or alternatively, energy efficient synapses may display signatures of Bayesian inference without actually using Bayes to reason about uncertainty. So what that means, I guess, is that there's this Bayesian inference as the structure that's universal, and we talked about universal computation several weeks ago, where, whereby this Bayesian inference has a structure that can be replicated. It's not using Bayes of any, it's not consciously using Bayes, or I guess there's not like a formal Bayes mechanism. I don't know how you would design that, but basically it'd be like a neural circuit that was formulated kind of like the Bayesian inferential rules, that they still display these kind of signatures. So in other words, like if you had a system that just basically took past inputs, brought into the present, integrated it with present information, that would be a signature of Bayesian inference. That's not necessarily using Bayes, but it's Bayesian-like. I'm not sure. I guess the implication here is that evolution, that the system would evolve towards Bayesian inference, but I'm not really sure. I'm not really comfortable with some of the language you're using here, but or at least I can say that it's not like necessarily something that would be. I think there's a little bit of this anthropomorphism there. But anyways, so this kind of talks about energetic costs and kind of considers them in terms of this sort of computational model of the brain. And so this is why I think this is really interesting. And then they implement this in an artificial neural network to show that these are theoretically plausible. So that's the first paper. And I'll post these in the Slack so we can follow up on them if we want. The second paper is actually from a group of people at Santa Fe, I believe. Jeffrey West, James Brown, and Brian Enquist. Actually, Brian Enquist is now from Santa Fe, as far as I know. But I think an evolutionary biologist. James Brown and Jeffrey West have done a lot of work on scaling and scaling, like allometric scaling and things like that. So they have this idea about using scaling laws to predict biological growth and other types of biological phenomena. So they use these kind of 3/4 power laws, which are like these linear relationships that you can, or I guess they're slightly nonlinear, to predict growth and changes in biological systems. So that's kind of a cottage industry for them. In this paper, they talk about a general model for ontogenetic growth. And so this one actually relates to sort of energy use during development and how that part kind of fits into some of these allocations of metabolic energy. So the abstract reads, several equations have been proposed to describe ontogenetic growth trajectories for organisms justified primarily on the goodness of fit rather than on any biological mechanism. And again, this goes back to this idea of is a biological mechanism, does it sort of approximate these sort of equations, or does it actually have a model of these equations and it uses that to produce the output? So it's kind of a meta question, but basically this equation here, which is actually a scaling law, does nature use this in a way that's does it try to approximate this, or does it approximate this? Or is this equation just something we've built that kind of describes the system, and there's actually some other set of mechanisms that are, involving, other types of things, and whatever this equation is describing is simply not relevant to anything in biology. It's just a construct we make to describe it. So, it's an important point because, we talk about metabolic scaling, we take these variables and parameters and we put them together in a set of relationships. Those relationships are just for our understanding necessarily. They're not necessarily what's going on in the biological system. The mechanisms might be totally different in terms of their structure and how they're related. So it's something to think about. So here we derive a general quantitative model based on fundamental principles for the allocation of metabolic energy between the maintenance of existing tissue and the production of new biomass. So this is an interesting point that often maybe gets ignored. Whenever you have, and it's not just in development, but generally in maintenance of the body in terms of homeostasis, the body will, if there's a shortage of energy, the body will protect existing tissue first, or protect the core processes first, and then everything else is secondary. So, like sometimes if children don't have enough to eat, they don't grow taller. They, their core metabolic needs are met, and then their height gets sacrificed, so they don't grow as tall. There are other cases where, in plants, if there's a drought, they'll grow smaller, or they'll still function as plants. They're still alive, but they're smaller. This idea of growth is like, sort of the abundance of energy rather than like the existence of energy. Things are sort of moved towards these core pathways first, and then you have growth. We thus predict the parameters governing growth curves from basic cellular properties, and derive single parameterless universal curves that describe the growth of many diverse species. So this is the idea behind allometry, where you have these curves or these functions that describe this. You can predict the size of any organism given like a certain amount of length of time that it can grow, given a certain amount of energy that it has available, and so forth. And so you can actually plot this out in a graphical relationship. So this is kind of their cottage industry, though. They've been talking about this for years. And it's not just biological systems. They've talked about the growth of cities and the growth of other kinds of things. So this is something that can be, and again, it's based on energy. So like cities grow to a certain size, or you have a certain size distribution among cities in the world or in a country based on the energy that they consume. So if you have a place where, it's a trading center, it becomes it generally becomes a bigger settlement. And so if you look at a lot of countries, they conform to the scaling law where, larger cities are rare and smaller towns are more common. And that's because of the flow of energy. You also see that in ecosystems with like river systems, or even in trees where you have branching systems and trunk systems, things like that. And this is all really driven by energetic balance. So they have this model. It provides the basis for deriving allometric relationships for growth rates and the timing of life history events, which means that it manages when things happen in development. And so, like, if you have a shortage of energy, things are put off, things are slowed down in development. So maybe you don't grow as large or as tall if you have a shortage of energy, but you still are able to survive. And that's the idea. And so this happens across species too, where you have different species that have longer periods of growth or greater access to energy. And so there's this curve can predict all of that. So that's another idea about, kind of in this area. The third paper is, the title is metabolic rate a universal pacemaker for biological processes? So now we're getting out of this idea of, well, I guess we're still in this idea of having like a statistical sort of model imbued in nature, or using a statistical model to describe what's going on in nature. So this is about metabolic rate being a pacemaker. And so pacemakers are things that keep time. So, your heart has a pacemaker, and you can actually implant a pacemaker in a heart. And there are pacemaker neurons in certain structures in nature that are like these muscles that twitch on a regular basis, and they get a signal. And then other things entrain to those pacemakers. So, you have like cardiac pacemakers, but you also have, circadian pacemaker. So you have a circadian rhythm, there's a pacemaker that keeps sort of a time, and then, things entrain to that time period. So that's where they're going with this. So they're arguing that metabolic rate may be a universal pacemaker. Let's see what they say, the abstract. The abstract reads, a common long-held belief is that metabolic rate drives the rates of various biological, ecological, and evolutionary processes. So this is what we were just talking about in the last two papers. Although this metabolic pacemaker view is assumed by the recent influential metabolic theory of ecology, may be true in at least some situations. For example, those involving moderate temperature effects or physiological processes closely linked to metabolism. And examples of these include heartbeat or breathing rate. It suffers from several major limitations. So this is a critique of this idea. And so the number of these limitations are: one, it is supported chiefly by indirect correlational evidence. So, for example, the paper we just talked about with terms of allometric scaling, this is a correlational piece of evidence saying that body size and temperature scaling, that you can predict this across a range of contexts or organisms or whatever, is correlational, and so it's not as strong as we would like. It's not causal necessarily. You can't always observe, you're just kind of predicting. Sometimes you don't observe all of the cases, all of the counterfactuals that might exist that prove the opposite. Direct mechanistic or experimental support is scarce and much needed for this. So this is a direct critique of the last paper we talked about. Two, it is contradicted by abundant evidence showing that various intrinsic and extrinsic factors, so for example, hormonal action and temperature changes, can dissociate the rates of growth or rates of metabolism, growth, and development and other biological processes. So in other words, what he's saying is that hormonal action and temperature changes can also have a role in this. And when we talk about energy balance and metabolism, that often almost serves as a stand-in sometimes for other things we don't fully understand. So we can just say, well, the rate of energy is high or low. Well, you have to measure the input of energy. If you're not measuring the input of energy precisely, then it may be something else that's confounding that, and it may not be the right interpretation. Three, there are many examples where metabolic rate appears to respond to, rather than drive, the rates of various other biological processes. So this is, like we talked about causality this summer. We talked about sort of the directional causality. So, is it that metabolic rate responds to or drives the rates of other biological processes? Maybe metabolic rate responds to other biological processes. So, for example, they give examples of ontogenetic or developmental growth, food intake, and locomotor activity. If these are things that, are driving metabolic rate, so for example, if you can get food more easily, then your metabolic rate is higher. And so, that's a sort of a circular causality there. It's hard to disentangle just by saying that energy drives this process. Four, there are additional examples where metabolic rate appears to be unrelated to the rate of a biological process. So metabolic rate can be unrelated to a biological process. So for example, in aging, which is a sort of, can be environmental inputs, influences, like, mutational rate or whatever, just time that goes by and your body isn't able to respond like it used to. Other types of things like cancers or things that impact your ability to regenerate. Circadian rhythms, of course, where, you're entrained to the environment, to the photic environment. And molecular evolution. So molecular evolution is decoupled from the physiology and the need to use energy. It's, it's different. So these are things that are unrelated to the rate of a biologic process, but this is where metabolic rate doesn't necessarily play a role. So how do you account for these things? The fourth one is the theoretical foundation for the metabolic pacemaker view, which is this idea that there's this central pacemaker that regulates metabolic rate, focuses only on the energetic control of biological processes, while ignoring the importance of informational control, as mediated by various genetic, cellular, and neuroendocrine regulatory systems. So this is where they're arguing that informational control is separate from this energetic control. In the first paper, they talked about information as sort of this Bayesian process, and that it was sort of imbued in the metabolic aspect of that system. What he's arguing here more is that informational control is separate and apart from energetic control, which is, of course, they could be intertwined, but you have to, again, disentangle the role of each. So this is where the critique stands. I argue that a comprehensive understanding of the pace of life must include how biological activities depend on both energy and information and their environmentally sensitive interactions. So this is again pointing out that these are interacting things, energy and information. And it's not good enough to say like energetics is also controlled by some informational processing, which we don't understand, but if we just take it together, that just explains everything. That's not really what we need. What we need to understand is like the energetic balance, but then informational processes, and if they're operating separately, and then especially if they're like there's a circular causality there, then we need to understand that to really get a handle on these problems. So this holds true if whether or not you hypothesize that it's like a sort of a scaling function or a Bayesian mechanism or whatever. This conclusion is supported by extensive evidence showing that hormones and other regulatory factors and signaling systems coordinate the process of growth, metabolism, and food intake in adaptive ways that are responsive to an organism's internal and external conditions. So we know that from our embodiment stuff that this is a common thing that it's not as common. It's not as commonly thought of. It's not as commonly assumed as we like to think. I think a lot of times people write papers that, especially the first paper, they didn't really account for embodiment. It was just kind of like, well, we can take this synaptic relationship, plug it into an artificial neural network, and get this goal response. But synaptic relationships have a lot of causal factors that go beyond like just the synapse. So there's this embodiment aspect too. We don't need to go to this whole organismal level, but it is interesting to think about when we talk about the mind and brain being driven by not just the brain. Like Jerry Fodor used to argue that the mind does not exist below the neck, and so everything else in the body doesn't matter. But of course, we know it's probably not true. But to what extent that is not clear. But I think we need to have a good framework to say what that is. Metabolic rate does not merely dictate growth rate, but is co-adjusted with it. So growth rate is, maybe the influence of other things. You can have a growth, obviously metabolic rate can constrain growth, but it doesn't necessarily dictate it in the way that you would think. There are a lot, there's a lot of energy storage. But it's important to remember that metabolic rate fluctuates. It's not just this like upper bound. It fluctuates over time, especially, we think about like someone who doesn't grow to their full size that they would normally be. That can be driven by like extreme cases. So like if you are constantly experiencing like drought conditions or starvation conditions. But even then, there are cases where you can have a response that's adaptive to those conditions. So you evolve, or you have like an adaptation where you can optimize your energetic ability or your capacity to use energy more efficiently. So some organisms are very efficient at using the energy that exists in their environment. So there are ways to there are ways to adapt to that. Energy and information use are intimately intertwined in living systems. Biological signaling pathways both control and respond to the energetic state of an organism. This is kind of what I was getting at, although this is more about like, signaling pathways, turning up and turning down the production of certain proteins. And there are different ways. It's not just a matter of like, we can count the energy flux and then make a general statement about, the outcome. There are a lot of little knobs and dials in here that can be turned. This review also reveals that we have much to learn about the temporal structure of the pace of life. Are its component processes highly integrated and synchronized, or are they loosely connected and often discordant? And what causes the level of coordination we see? These questions are of great theoretical and practical importance. So this is an interesting point here. Are its component processes highly integrated and synchronized, or are they loosely connected and often discordant? And I think that's important because like synchronization is often a kind of a thing that we forget about with respect to like a response. Synchronization can be like produce a certain outcome that if the system were less highly integrated, it would not. So this could be true of behavior, but it could also be true of physiological state. And so there's a lot of variation there we need to kind of understand. And this is, I think, one parameter that really kind of helps us understand that, like, if something is synchronized versus if something is loosely related and desynchronized. Certainly, if you're into dynamical systems, we know that there are like these order parameters that kind of describe that process. But other than that, it's like, not really, we don't really talk about too much in other areas, especially those that aren't, dynamical systems related. Okay, so we had some comments in the chat here. Okay, Hall's drawings are incredible. Yeah, he did this on his kitchen table or something like that. So he didn't have like the benefit of modern like super lab money. It's like he used to go back to those things. So it's like the benefit of like having, kitchen table science, literally, is that you can do these kind of things. So yeah, and so we have any questions or comments?
No questions. Just processing a lot from everything today.
Yeah, it's a lot, but yeah. The three papers there were kind of like a broad overview, just not just energetics, but I think a lot of the topics we've been talking about. Yeah, so I don't know we'll follow up on that or not, but yeah, I think there's a lot there, like with energetics and with development. We don't talk too much about energetics in our work directly. We've talked about some of our developmental techniques, and energetics is kind of implied, but not directly put into practice. So,
I think that's sort of like an area for, I don't know if it's fair to say the methods project for the cognition futures itself, but like there's something in terms of exactly what you said, development, like there's a space for that to be I don't know. That needs to be incorporated into it,
yeah. Then, I'm working on this long-suffering presentation on information and energy. So, like, we were talking about information, like, we're talking about information and talking about thermodynamic entropy and how they're kind of related. And this is like a thing that I've thought about for a long time, but I've been putting slides together on this. So you have things like Maxwell's demon, you have things like, the application of energy to life, the application of information to life. So I'm kind of going through all that now. I'm still working on it, actually. It's like this massive presentation. I'm going to break it down to a couple parts. And eventually this is going to come out on YouTube, I think. But I'm still working on it. But there's a lot of food for thought there, which I haven't shared with people in terms of like, computational agents and then this aspect of information and energetics. So the idea is that, entropy governs like a lot of physical systems. Life is a physical system, but life also has information, and the information can overrule or supersede uh, thermodynamic entropy. And so there have been people historically who have thought yes. And one of the mechanisms that we have is the Maxwell's demon, which basically says that you can have a system that is subject to thermodynamic entropy, but you can also have something that is has some informational gain. In other words, you can have a system that if you open a chamber door between two chambers with randomly distributed balls that move around randomly through excitation, that if you do that just right, if you have enough information to make the sort of the selection process work, you can sort the balls into two independent and mutually exclusive categories. So that if you have red balls and blue balls and they're well mixed, you can have this situation where they can be sorted out over time. And so this is exactly the opposite of what thermodynamic entropy predicts, which is, or the second law of thermodynamics predicts, which is that the system will either stay random or evolve to randomness. And so this is just kind of a thought experiment, but you can like apply that to other kinds of issues, especially where physical systems interact with informational systems. And so that's where that's going, and it's a very circuitous route. I'm still working on it. I don't think I'm going to solve any big problems, but I did want to get that out for people.
No, that's really cool. Even just the way you described it was helpful for me just to think. Even just like your 5-minute preview has given me a useful context for thinking about things. So I look forward to that full one too.
Yeah. All right. Well, I think that's all for today, unless anyone had anything else they wanted to mention.
No, that's all for me. I'm taking a bunch of notes, and with a lot, Amanda contributed a lot.
Yeah.
In the Notion as well. So it's a good Notion page today.
Oh yeah, this looks really good. I'm looking at it right now.
Oh, nice.
Oh yeah, this is going through. Yeah, we don't revisit our Notion enough. We really should do some like sort of secondary sort of analysis of the Notion pages, because some of these have a lot of information in them that we could push forward on this.
Yeah, this one's really good. The last few haven't been, or like I missed a meeting or something. But when they're really good, they're quite helpful. So I'm trying to. I don't always do a great job of saying, hey, let's all take notes and like screenshot stuff and share it. Like just throw it in there, because the more we can do that, the more useful it will be to kind of put information into the system and
defeat entropy. Yes.
We can ping off of it better. So
yeah.
Nice. Okay.
All right.
I'll talk to you all next time.
Yeah. Have a good week. Thank you.
Bye-bye.
Talk to you soon.
Talk to you soon. Bye.